from answer.
Yes. So have you solved that problem?
Yes, sir. I tried to solve and I got some answer.
Mm-hmm. What is that? Let me see the problem first once. Okay. So this was the problem, right?
Yes, sir.
Yeah. So what answers did you get? Let me check the first part. So first part we solved uh, with flux. How much flux per pole? So that came out to be 1.56 milliweber per pole. So was that answer correct? Did you verify it?
No, sir.
Okay, so you could have verified it as well. Other thing is that in part B, what is the current per path? So current per path will be total armature current divided by number of the paths. So that I think it should be very easy.
Sir, it was 13.02 ampere.
13.02 ampere. So total current was how much? So total current, do you know how to find? It is not directly given in the problem. Actually, I must have told in the last session as well how to calculate that.
Sir, because they did give the power and voltage, so we
Yeah,
can calculate current.
certainly. So that is a way. So 20,000 divided by 120 volts. Actually, I think from your devices some echo is generating. So are you logging in with two devices? Yeah.
With two devices. No, sir.
Okay, so some echo was coming, so that's why. Okay, no problem. Now it is fine. So this current would be equal to how much? Yeah. How much this current would be?
208.33 ampere.
208.33 ampere. Now, we need to find out the current per parallel path. So current in parallel path, in each parallel path, how much it would be? 208.33 divided by 8 pole and
16.
lap 8 pole.
16.
Okay, okay, yeah. So it is 16. How you are saying 16?
Sir, because it is a duplex lab bound binding. So in this
Exactly.
binding,
Yes. So in duplex lap winding, it would be uh number of parallel paths is equal to number of pole, and since it is a duplex winding, so we will have 16 number of parallel paths in total, right? So it would come out to be how much?
sir, 13.02 ampere.
13.02 amps. Yes. So I think we are done with the part B, right? Part
Yes,
B
sir.
we are done. Part A we did in the last session. So part C, what is the induced torque in the machine at the rated load? How much do you expect?
Sir, 66.33 I calculated.
6.33 you calculated. Okay, 6.33 Newton meter. Torque you calculated. How?
Sir, 66.
66.33. Okay. So how?
Sir, the by the formula of torque,
Huh?
T is equal to phi Z IA by 2
Huh.
pi multiplied by P by A.
Okay, so basically you are saying that E into I, that is the power divided by speed, right? So torque
Yes,
will
sir.
be equal. Yeah, that is correct. Yeah, EB IA by omega, and EB is nothing but K phi omega into IA divided by omega. So here omega and omega will be cancelled, right? So of course we will be left over with K phi IA, and which what is that the expression of torque? We already know it, and the value of K is ZP by 2 pi A, right? To phi into IA, and we have calculated everything. So you just need to plug in. Z is equal to how many conductors? 12 AT, right? 12 AT conductors. And to number of pole is 8 divided by 2 pi into 16 into flux we have computed in part A, that is 1.56 milliweber per pole.
Sir, I think this part were wrong.
Which part?
Sir, this flux.
Flux, okay. Okay, how much is that?
Sir, it is 3.125 milliweber.
3.125. Okay, let us. Is there a mistake in calculation or anything else? Expression is correct or not?
Sir, expression is correct. I think there is a mistake in calculation.
Calculation. Okay, so then ignore that calculation mistake. So we have updated that value with 3.125. Okay, so thanks for pointing that out. Okay, uh, so we wrote here K, this phi is 3.125 into IA. IA is nothing but 208.33. So how much will it be? So you told this answer right earlier.
Sir, same answer is coming same.
Oh, with updated value of flux as well. Okay, so because it is in milliweber, so that's why it might be coming. Oh, so it's- is that right?
Yes, sir.
Okay. So I think we are done with the part C. Now coming back to the part D. How many brushes this motor must have?
Sir, 16.
16. Okay. According to your logic, it makes sense, but in actual scenario, it will be 8 because the number of brushes are equal to number of parallel paths. That you are correct, 16, but it is a duplex wound, right? So in that case, the width of the brush, width of the brush, one brush can, one brush should be enough for two coils, right? Because both of the coils will be connected to the same slot. So in one slot, there will be two coils, and with each slot, the commutator will be connected, and with that, single piece of brush would be enough for one side of the coil. So the number of brushes, let me write down for you, the number of brushes are equal to number of poles in case of lap wound. It is irrespective of plurality of the winding. Okay, and same, it will be equal to 2 for wave wound, right? So this might be a tricky question, but in physical sense, uh, a pair of brushes would be sufficient for a coil, whether it is a a simplex wound or duplex wound or triplex wound or quadruplex wound, it won't matter. Is that right? So take care of
Yes,
this
sir.
one. Yeah. So
Sir, answer is 8.
answer is 8. Yeah. So answer is 8. But it should have wide enough to, stretch across. But number of commutator segments, how much? You have to first figure it out. How much? How many number of commutator segments will be required?
Sir, I think 64.
64.
Not sir,
64.
64.
How? So number of
Sir, 32.
commutators are essentially number of slots, right?
Sir, 32.
32 commutator segments. Again, question is still why.
Sir, because we have 64 coil, and since it is a duplex lap bound, so
Uh-huh.
each slot will contain 2 coil.
Uh-huh.
So that's why the total number of coil is 64. So we need 32 slots.
Okay, so the reason is that we have 64 coils, but we have 32 slots. So one commutator would be sufficient enough to fit into the number of two number of coils. So yeah, 32 commutators will be required, or I guess let me think. So there are 64 coils. They are duplex. Uh, am I audible enough? I think
Yes,
I
sir.
have lost the. Okay, okay, thanks. So yeah, so that was that part, and the final part was, if the resistance of this winding is 0.011 per turn, then what is the armature resistance of this machine? So the resistance of one turn is 0.11 ohm, right? So how much will be the armature resistance of the machine?
Sir, 7.04.
7.04 you are saying, okay. You let me know the expression as well.
Sir, since we have a number of turns is 64.
Yeah,
And
just a second. So number of turns is equal to,
no, sir, number of
yeah,
coil.
and
Number of
number of
coil is a
coil,
64.
yeah. So number of turns, how much it will be?
And each coil has 10 turns, so a number of turns will be 640.
640 turns. Yes, that is fine.
And
So now,
each
yeah.
each turn has a
So total number of turns are 640, right? And total number of parallel paths are 16, right? So number of turns per parallel path. So in the question, it is provided that resistance of one turn. Okay. So if it is given for one turn, so first we need to find out how much number of turns are in each path. And then we have to divide it by number of paths, right? So number of turns per parallel path would be 640 divided by 16. So it will be 40 turns per parallel path. And the resistance for the path would be how much? Would be how much resistance for the path?
0.44 ohm.
0.441. Yeah. So essentially, this resistance for the path for for one turn, the resistance is 0.011 ohm, right? So in each path there are 40 turns. So that will lead to 0.0441 ohm per path. And after that, total resistance will be equal to how much? R path divided by number of parallel branches, right? So number of parallel branches are 16 again. So it will be 0.44 divided by 16, and it will be equal to 0.0275 ohm. This will be your total armature resistance. Any doubt in this part?
Okay.
Okay. So where did you find out yourself committing mistake?
Sir, in this resistance problem.
Resistance problem, you might have committed mistake, and other part is here.
Other part was
This
correct.
okay, other parts were correct. Okay, fine. Then it is good enough. Yeah. So as I promised you that I would show you some simulation file, right? So that you will visualize how the flux lines flow. So let me show that to you. Okay. Let me stop presenting this screen and connect it to my top. So are you able to see my screen?
Yes, sir.
Okay, great. So I hope you are able to see the machine 2D model. So now, see, this red part is nothing but
Yoke.
this rotor. So yeah, yoke. Yeah, you are correct. A stator lamination, which you can say yoke or anything, or back iron, or basically it is a stator core, right? And this green portion is what?
Poles.
Yeah, they are poles. So basically, we have two ways to create number of poles. One way is to wind the some portion of electromagnets or some portion of permeable material with electromagnetic coils, or other is that you just paste the permanent magnet so that it will create magnetic flux. And this magnetic flux that will originate from these permanent magnets. There, how many poles can you see on the screen? I guess you are able to see the 4 poles, right?
Yes, sir.
So yeah, so those 4 poles must link their flux to the stator coils, right? So this blue portion is nothing but your rotor core or armature core, you better say. So armature cores are in blue, and this rotor cores are, or field core, you can say, that is in red color. And these yellow sections are nothing but the armature windings, which okay, so let me show you the radial pattern. So these are how the armature windings are being wound on the armatures, right? So just you see this machine I have designed with 4 parallel paths, so you can see the one parallel path, right? And the throw is nothing but the slot per pole. So this cross is coming. This cross is at 1, and this dot would be after 4 slot, 1, 2, 3, 4. So this overhang or this coil pitch is nothing but your slot per pole. So we have taken, you can see how many slots and how many poles. Poles we can easily figure it out. There are 4, and the number of slots, that is armature slots, if you will count it, you will find that there are 20 number of armature slots, right? So if you do a 20 by 4, you will find that will be equal to 5, and you can see the that's the way how we wound. So it is coming out of 17 and it will go to 18, 19, 21. So it will skip the 4 slots and it will go into the 5th slot. Are you able to see? If you are not comfortable leaving it, please let me know.
Yes, sir, we can see it.
Okay, great. So one path would be originated from these squares, right? These many, and others would be from these paths, right? Path 2, and next will be path 3, and last one would be path 4. So these are the fashions by which we can want a distributed winding. And if you want to see the linear pattern, so this is the linear pattern. So path 1, path 2, path 3, path 4. So if I show all at once, then this is how it will be looked like. Right? And number of brushes will be equal to number of poles. So they are the total number of brushes are 4. Okay, some section is overlapped here of the last brush. So this is how from this view, if you just want to focus on winding, so this is how we do the winding, right? So yeah, any question in this section from winding section? So yeah, one
Sir,
thing I
this
wanted
top
to,
and
yeah,
bottom binding will not get affected by the flux.
top and bottom. So you basically you mean by these sections, right? These sections.
Yes, sir.
Yeah, actually they are not active winding. They have to be there just to finish the winding. So they will not contribute into flux, because flux I will show you in a while that how flux will flow. So flux will basically flow radially. If you see, so they will flow radially. So to link the flux in axial view, let me show you 3D model. So this is how your total machine will look like. So let me remove the end winding. So you see, I just eliminated the end winding, and end winding. Now I will again bring back that end winding. So end winding are not linking with these cores, right? So their flux will go nowhere. So basically they are leakage flux. Basically they will be included in leakage, you can say. But yeah, they are not contributing in any torque generation. So we try to maintain overhang as low as possible, but that creates some another drawback. So you have to gain something and lose something. So here you are maintaining very nice profile of back EMF and all, but here you will have larger overhang, and in concentrated winding you will just wound the coil in a slot. So your in winding length would be reduced drastically, but that creates so many harmonics and all. You might have studied or will study in synchronous machine section that winding factor terminology and the harmonics associated with those winding factor. So these distributions are basically sinusoidal kind of thing, and but if you want to make a concentrated coil, then that will lead to certain harmonics in the machine. So is that clear, Deepak?
Sir, these 4 brushes connected to a single supply, common supply.
These four.
Sir, voice is not coming.
What is coming?
Voice.
Sorry, I am not getting you.
Sir, your
Could you
voice
please
was
repeat?
not coming.
Okay, now is it coming? Now is it proper?
Yes, sir.
Okay, great. So these are the commutators, and these gray are brushes. So you see these commutators will rotate and brushes will be there. So whatever the position your armature would be, that much supply we can extract or we can supply to the machine, right? So this is how it will look like. And if you just want to see the lamination, so this is how your stator core will look like. And these magnets will be placed like that. So they will be pasted on the surface. You can see.
Sir, we used a permanent magnet.
Permanent magnet, yes. So as I told you in the starting of this model, that you can create field by any way, right? Field winding or permanent magnet. So electromagnet is very weak source of magnetic field because you have to wound, you have to manage, right? You have to manage the current supply. You have to also take care of the heat flow. So nowadays it is obsolete almost, that field wound. But you can place permanent magnet. You are not providing any supply, right? It's just creating magnetic flux by its own.
Sir, strength of permanent magnet is always same or it will decrease?
It see it as I told you, to reduce the strength of magnetic field in this permanent magnet, you have to provide armature current appropriately. So if you want to reduce the strength, you have to apply armature current in such a way that it will demagnetize this permanent magnet, right? So that's the way. Or otherwise, if you want to increase the magnetic field, so you can uh, increase the magnetizing component of the current from your supply, right?
Okay.
Yeah,
Sir,
Neeraj.
what is the lifeline of this magnet?
Yeah, Deepak, you were saying something?
Sir, how many time up to this magnet will work or it will automatically destroy or not work?
Uh, See, that time of period is very high. Actually, we do not worry about that because that is sufficiently high. The work, the temperature dependent degradation. So, as you increase temperature after certain point, 150 degrees centigrade, some of the portion or the entire portion of these permanent magnets may get demagnetized permanently. So then it will not be of any use. So as it again, which is very difficult for to magnetize such a high magnetic strength materials, right? Or other way is to, you have to manage. So it is a work of designer that they have to operate these motors or generators at certain operating point such that it does not face those challenges. So those are the concerns that we should worry about. Did that answer to your question?
Sir, your voice were discontinuous, I think. I did
Is
not
there
got
any
complete answer.
Neeraj, was it hear me properly, or is it problem with my internet connection?
Sir, I also was not able to hear you clearly, sir.
Okay, so I think there is issue with my internet. Let me just reconnect with. So is it fine now? You just stop me at that point where I my voice will start breaking, right?
Okay, sir.
Yeah.
Sir, you were saying that temperature, I think you were saying temperature will not exceed with particular value.
Yeah. So I was saying, I'm audible now, right?
Yes, sir.
Okay. So what I was saying that the point of worry is not that the life cycle of these permanent magnets. And the point of worry is that these permanent magnets, if you do not operate it, below certain temperature limit, then the probability of those permanent magnets getting demagnetized permanently is very high. So once your permanent magnet will be demagnetized, then it will be very difficult to magnetize it again. And to magnetize it again, you have to, take it out from the stator core or motor or this machine. So your machine will be of no use. Let's say you are using this motor in your electric vehicle. So then you have to remove the motor from the EV. Then again from the motor you have to remove a stator and all, and then again you have to supply very high strength of current to again magnetize it. And again, if your design is not proper, then there is high probability that this will again be demagnetized. So you have to operate in a way such that it should not get demagnetized permanently. Right? Did that answer to your question?
Yes, sir. Okay.
Mhm.
Sir, how this will demagnetize permanently by the temperature?
By the temperature, and that temperature will be generated from armature current. So if you are creating, demagnetizing component of armature MMF from the armature winding, then if it will be higher than the tolerance point of the permanent magnet, then it can be demagnetized.
Okay, sir. It will permanently demagnetize.
Yeah, so then it will be of no use.
Sir, then we have to take care of the temperature limit for this machine when
Ye-
during the operation.
Yes, yes, yes. So that's the main point. That's how we have to. You can generate any kind of performance, but to maintain that performance, you should have such or any particular kind of cooling mechanism that will extract the heat out of your windings and losses that will be generated during the torque production. So we have to maintain temperature below a certain point.
Okay, sir. Sir, please show the diagram where the flux paths were visible, sir.
Yeah, yeah. So I am coming to the flux path. So these are the flux paths, right? So let me just blow it up for you. So this is the north pole. Let me zoom out. So this is the north pole. Yeah, right. So almost half of the portion is going, and it will link to the south pole of the magnet, and through the magnet, through the magnet, there will be some leakage, right? There will be some leakage. They are again going back. So if you ignore those leakages, most of them are coming back to the stator. Oh, sorry, coming back to the armature or rotor. They will again try to link to the north pole. So it will come out of the north pole, go all the way through the rotor core and will come back again through the south pole and air gap. So these are the air gap you see. So in air gap, the density of flux will look like something. So we are mostly concerned that whatever flux are coming from the permanent magnet, right, they should cross air gap and link to this stator or tooth. Oh, sorry, why I am calling it a stator? Actually, armature or rotor core. So it should link it, and whatever leakage will be there, they are not desirable. So that's what. And let me just yeah. So these are the way, and if you do not want to see the direction, then this is the way your flux path will be look. So a total number of loops, flux loops will be equal to your number of poles, right? So you have 4 poles. You can see there are 4 poles, right?
Yes, sir.
Yeah. So this is how your armature will rotate, and your stator will be stationary. So field winding and permanent magnets will be stationary, and your armature will have to rotate, right, with constant air gap. So see, your flux are more or less uniform if you haven't provided any armature reaction, right?
Yes, sir.
So your flux lines are constant because of permanent magnet, and they are stationary. Had it been revolving, when it will come to synchronous machine, I will show you very good pictures of them. When your rotor and permanent magnet on the rotor will rotate, right? Because in synchronous machine, the scenario will be reversed. So in those cases, your field will be rotating and your armature will be stationary. So
Yes.
you can see the rotating magnetic field there. Here,
Okay, sir.
to produce DC or uniform torque, you should have, both MMF forces, armature and field MMF forces should be stationary to each other, right? This concept, I hope.
Yes, sir. There should be a constant angle between the two
Yeah,
fields.
yeah. So relative velocity of them should be zero to produce uniform torque, right? So in DC machine, we have, you know, zero speed of field winding. So, and we have some speed of armature winding. So we are creating such kind of mechanism of linking the flux that both fields should be rotate at zero speed. So these are when this scenario, this particular flux linkage you are seeing, when no load, no armature current has been supplied to this motor. But here field winding is stationary, so now we have to bring back the armature winding field to a stationary. In synchronous machine, our field winding rotates, right? To rotate the armature winding field or a stator field, what we do, we provide three-phase balance supply to the in 120-degree phase displaced in space. So that creates rotating magnetic field. So that rotating magnetic field will rotate by the nature of supply we provide to the stator, and that will rotate at synchronous speed. And your this rotor, permanent magnet and rotor, that will try to link that, and that will also rotate at synchronous speed. But here we are providing DC supply, right? So hence it will be a stationary, and anyway your stator is already stationary, so both are stationary. So that's the principle of torque production. So let me show you some graphs how voltages and currents will be uh, provided. So this is the back EMF. This is the back EMF. So it is not an entire DC. There will be some ripple, some transition you can see. So uh, this flat point, almost flat point, is the your field coil pitch or magnet arc. How much magnet arc is there? So you can see those magnet arcs are how much 140 degrees. So it will be equivalent to 140 degree. Yeah, and these are transitions. So and for path one and path three, you can see this is for path one and path three, this section, and that is a positive. And for path two and path four will come be from the negative section, and overall voltage will be path one minus path three. So overall will be add up, and that will be equal to, peak value will be equal to approximately some 400 or something. So this is how your air gap flux density that will look like. Let me just simplify it for you. So it is not a flat DC. We want it, a flat portion here and then transition, then flat. But these are not flat. Why are they not flat? Do you have any reason?
Air gap and this armature face is not smooth, sir.
Yeah, so basically our stator slots and all they are not perfectly uniform, right? So basically apart from cores, they are just equivalent to air. So these are not uniform permeable path. So they create this distortion in our air gap flux density.
Okay, sir. The main reason is the varying reluctance.
Yes, exactly. Uh, so
This graph is due to the field poles, sir.
due to field poles only. I will show you when armature field will come, how will it look like.
Okay, sir.
Okay, so is there any doubt in this whole model with no load?
Sir, in
So
DC motor, both the fields are constant.
in this model, just permanent magnet field flux are available. We haven't provided any armature MMF or any armature current or any supply till now. So that's why you can see
This
here
is
this is with only permanent magnet, only field coils.
okay, sir.
Okay, so you can one very interesting thing I wanted to point it out. You can see those flux density are not very uniform. Somewhere it is red, somewhere it is green. So you on the legend you can see that these red portions are near to saturation 2.2 Tesla. They have exceeded the saturation limit, right? So those will be portions which will create heavy losses, and they are reducing the permeability of this core as well, right? So if you are a good designer, you wouldn't allow it to go up to 2.2, yeah, until and unless you have some other motive to pursue, like you have some constraint that you cannot go beyond this limit. So what should you do? You should increase this width of a stator core, okay, and that should be sufficient to reduce. Okay. So and these portions, blue portions, they are unutilized, right? They are less utilized. So you can increase the diameter of shaft, and you can make a hollow shaft such that those portions should also get utilized. So this is another thing, that neither should you underutilize the core, nor you should overutilize the core. Okay, so these tools are also, you can accordingly vary and see what would it contribute to. So let me bring back the armature reaction
Sir,
one.
sir, sir.
Yeah.
Sir, if this core will go to the saturation mode, then what will happen? It will produce a losses.
Yeah, it will create huge losses, no?
Sir, how?
What is the expression of iron losses?
Eddy current losses and hysteresis losses.
Yes. So in the expression, PM comes or not? Maximum flux
BM.
density.
Yes, sir, it is coming. It
Uh,
it it comes.
if maximum flux density expression is there, and how does that vary? Approximately a square of that, right?
Yes, sir, in case of eddy current load, it is square.
In hysteresis also, it is close to 2, a Steinmetz constant, right?
Yes, sir, it is. Yes.
So for, let me show you when I bring this loaded condition, how much losses you can see in that model. Okay, since it is on no load, so there is no point of discussing losses and all. But if let me bring back the things. So this is the model with we have provided 5 amps of current, and I have kept 3000 rpm of rotation speed of the machine. Okay, and I am considering 1.5 voltage of brush voltage drop and all, and same, the windings and all are same. So these are the pattern of windings as I have shown it earlier. Now let me bring back the results. So now you can see, first thing is that you should visualize the flux paths, right? Since they are steady, but still with armature and field. How does they look? So after providing armature MMF, still the flux paths are steady. So that's how our constant torque will be produced. And but some variation in leakage fluxes you might be able to observe during the rotation. So they are there, yeah.
Yes, sir. Sir, I have one question, sir.
Go ahead.
So, sir, for calculating the losses, sir, the expression also involves frequency, sir. Here, there
Yes.
is their field is constant. It is not varying,
Yeah,
sir.
yeah, that is very, very good question. Yeah. So you mean to say that all the frequency dependent losses should be eliminated from this, right?
Yes, sir.
But yeah, that is a very good question. So I will explain that in a while. First, I will show you some data. So you can see this software will provide detailed analysis of how much losses are happening and where they are occurring, right? So you can see DC copper loss. First, let me show you some output. So this design has been done on for near to 1 kilowatt, 1000 watt, right? So input power is near to 950 watt, and output power we are able to achieve 907.95 watt, which, and if you see the efficiency of the system, which is above 95%, which is very good. Okay? For this power level, this efficiency is very good. But how we are able to achieve that? Because of permanent magnet. If you had certain field winding, you would have observed for this power level, even induction motor, PMSM, BLDC, any motor, it is very difficult to achieve this level of efficiency. But we have over designed the machine. So one, we have the tendency to look any bright feature of any equipment, but we ignore other things. So generally, if you see advertisement of any technical or anything, they highlight their salient features in terms of their advantages. they will hide, and it is a it is an very good approach of marketing, that they hide their drawbacks. Anyone would want to hide their disadvantages, such that their models will be sold enormously. But here we are able to achieve such efficiency, but we have over designed the machine. So you can see this weight of machine is 9.23 kg. That is very high. So this much weight is not desirable for such a output. And I will come to your question, Neeraj, why we are having this frequency dependent losses. In the meanwhile, you can also think that what is the reason. That you can see graphs. From the graphs, we have air gap flux density. So the square wave air gap flux density will have some fundamental, some first order, some third order, and so I will come to that. Other thing is that efficiency wise it is good, and but since this is a DC machine, right, and DC fields are there, we will experience some torque ripple as well. And along with that, let me show you some graph of current. So current we are providing DC, right? Terminal voltage and back EMF, I have shown you there are certain ripples, and this is the torque kind of waveform that we are able to see. So frequency term comes out from where? In this expression, this motor will rotate at certain speed, right? And that frequency is coming from the point that we do not have control on air gap flux density. Air gap flux density we are having in time domain. In a space domain, you have provided DC, constant DC. But in time domain, you are still receiving it in terms of fluctuating models. So your air gap flux density is not DC. Is it right? This air gap flux density waveform, are you able to see this is this, what would you say to these kind of signals?
It is periodic.
Periodic, yes. Periodic with certain point of time, certain time period, and it is not constant, right? So
Yes, sir.
it will have some frequency components. And but since it is a DC machine and we had to maintain constant field, such that, or that's why we have to use commutators and brushes. So essentially inside the machine, the operation is AC, right? Generation of back EMF and this air gap flux density, all of them are AC. But at the end or at the terminal, what we are providing is the DC component, or what we are receiving in terms of generator, that is DC component. But inside the machine, the operation is frequency dependent, right? Are you getting my point?
So please elaborate this point, sir.
See, this magnetic flux density will be generated near to the air gap, right?
Yes, sir.
Yeah. And that air gap will see this kind of flux density, and this flux density will have certain frequency. And that
Okay, sir.
frequency is nothing but how much? A speed that is dependent on the speed and number of poles.
Okay, sir.
Okay. And but that rotation and variation is happening inside the machine, not at the terminal. At the terminal, what you are providing to this motor, you are providing this current. This current you are providing.
Okay, sir.
But the arrangement inside the machine is done in such a manner that those has to be, alternating. Those has to be in alternating in nature. So that's the reason that we will see frequency dependent losses, because we have frequency. Okay, any other question from this section?
Sir,
Yeah.
sir, the current going into the armature is pulsating AC.
Current going in armature is
There,
DC. See
no,
this
sir.
one.
After the brushes,
After the brushes also it is DC. It's just that, distribution of those windings. Let me show you. Distribution of those windings are such that they create magnetic flux that is not DC, that is not constant. See, this distribution of this coil, right? The current will enter into this dot, that will be DC, and sorry, that will come out from this dot, that will be DC, and that will go into this cross, that will be also DC. But this distribution is in a space, right? This distribution is in a space, and when it will rotate, then it has to go through all the varying magnetic field. When it will go through the varying magnetic field, then your flux or magnetic domain is now not anymore DC. Right? Did you get this point? It may take a while to grasp these things, but that's the whole thing.
okay.
Sir, another student raised one doubt, sir. Please give him a chance.
Yeah, where is he? Is he in this session?
Yes, the person's name was Saw, Deepak Saw.
Okay. I thought both are same Deepak. Yeah, Deepak, go ahead.
Sir, he is typing in chat box, I think. Something.
Okay. Can we say that the armature core will see change reversal of flux depending upon whether armature core is in front of North Pole and South Pole? Yeah, so change of flux will be there. Let me show you. Obviously, change of flux will be there. If you are seeing in terms of time, so this is the nature of your flux. See, so from position to position, let me show it for you one path only. So this is the nature of flux, right? So one will be rising, one will be falling, and there will be some commutation period. Deepak, is it not possible for you to speak? Or you can chat. So this explains the dependent on. Yeah. You can conclude it in any way, right? I just had the way of understanding on the basis of flux density, which is the working principle of the machine, which is the core of the machine. Uh, that why, but if you can conclude it on the basis of rotation from the exterior point of view, that is also fine, as long as you are able to grasp the concept. That is good. Okay, is there any other question from you, Deepak, or from anyone? Okay, so I hope you might be able to visualize up to certain extent. the working of the machine, of DC machine particularly, right? So it might help you in gaining some insight, I guess. So why this helpful? Or why is there any doubt or anything you can say? Anyone? Okay. So actually, okay, you are having mic issue. Whether I can assume when the blast shifting from GNA is taking place in the direction of rotation for question number 10 to question number 13. Where is this? Where are these question number 10 and 13? I don't know. But there are things that it is in direction of motor in case of sorry, there. Let me first read this. The reason behind assuming the direction of the shifting from GNA to be is generating operating operation on the same. Actually, see, I haven't seen those questions regarding which you are discussing. I guess you are discussing about the current week's assignment. I haven't seen those questions because since we are not also uh, no, allowed to discuss them, but you are going in good direction that the direction reverses in case of motor and generator. In case of motor, I guess it is in the direction of rotation, and in case of generator, it is in the opposite direction of rotation. The shift of magnetic neutral axis to geometric neutral axis. So the region I think you want to know the region behind it. So, okay. So the region is simple, very simple. That whatever will be, magnetizing component in case of generator, that will become demagnetizing component in case of motor. So, uh, we have to shift. Let me draw. Mm. So I will stop presenting these simulation results and all. Okay, so let us get back to the theory portion. So see, this is your field MMF, right? This is your armature MMF. Now, the resultant will be something in this direction, right? Armature and field will be 90 degree to each other. But what will happen? So we have to, shift the brush axis. Brush axis are placed on which axis? Along the field or along the armature?
So magnetic neutral plane.
Magnetic neutral axis. So that is this axis, right? This is GNA. Now you have to shift your brush again by this angle. So this will have to be MNA, magnetic neutral axis. Such that the resultant flux will not affect those brushes, right? So those brushes should be, 90 degree to your resultant mmf, and that this direction will be in case of generator. So you have to rotate. Let's say your generator speed is in this way. So you are rotating the rotor in this manner. But in case of motor, you are giving the inverted supply. So if you are giving the inverted supply, your armature mmf will be something like this, in this direction. Now your resultant will be in some this direction, and again your MNA will be this direction. So since the armature current is inverted in case of motor with generator, so that's the reason that shifting will start to happen. Assignment 9. Okay, I haven't seen the particular assignment. In generator, it is in the direction. Okay, in generator, it is in the direction, and in the question, it is not specified the direction of brush shift. So direction of brush shift, it is, if you refer any lecture or any textbook, you will get the exact. I forgot in which direction it used to shift. So I think in generator it is in direction. Okay, but you want to ask in the case of generator whether it is able to rotate in the direction of rotation or against? Regarding that question, I am not sure, right? But I don't want to guess that part, but I'm not sure. You can refer any textbook or even in the Google also, it will give you the answer. Let me search it for you. Case of this. Yeah, so I just Googled it and I am able to see that MNA will be shifted in the direction of the rotation in the case of DC generator, right? And it will be shifted in opposite direction of the rotation in case of DC motor. Is that what you want, Deepak? All, do you guys have any idea what he is trying to ask, Deepak or Neeraj? Okay,
Sir, I'm
it
not
is
able to read the chat, sir.
okay. You are not able to read. He is not able to speak. What about you, Deepak?
Sir, I think he is confused that where we have to shift the brushes in the direction of rotation or not. I don't know in the question that is a generator or motor.
Have you seen the question?
Sir, I have one issue, sir.
Yeah, yeah.
Sir, the assignment whose due date is still remaining is not allowed to be discussed in these problem solving sessions, sir. I think.
Yeah, yes, yes, yes. That is
Sir,
correct. That's why I do not discuss.
sir, assignment 9 is live. It has a due date.
Okay, so I am not discussing any assignment since I haven't seen that, so I cannot discuss it. I I don't think. And see, if it is not mentioned that brush shift, then you can identify that if it is a generator, then the shift will be in the direction of the rotation, and if it is a motor, then the shift will occur in the opposite of the direction of the rotation. So you can solve that problem appropriately. And it is not necessary to mention in the question, you know. Okay. So
Sir, this brush shifting has been explained in lecture number 74 and 73.
Okay, okay. That must have been taught in very beautiful manner.
Yes, sir. I think Deepak should visit those lectures, sir.
Yeah, Deepak, you visit those lectures 73 and 74, and you can solve those problems. So for solving assignment should not be yours the primary concern. To learning the concept is more important than solving. You might solve assignment today on the basis of some facts and all, but if you don't know the concept, then in final exam, or not just for the exam, in any other stage, if you are pursuing your goal thing, or for any interviews also, you will be able to answer those in well manner. Okay, so let us come back to the session, right? So I had framed certain number of questions. Okay, just I will take a couple of minutes of break, then I will be back. Okay, is that fine?
Okay, sir. We'll wait.
Okay, thanks. Yeah, so I am back. Now let us start from a problem. Yeah, so read this data, okay, and we'll try to solve it. Yeah. So you can see the magnetization curve, okay, where according to the field current, the armature current, how does it vary, right? And these some data are given, the ratings of the motor, that is 30 horsepower, and current, rated current is also given, that is 110 amps. Field turns 2700 turns per pole. Armature turns are also provided. Now we have a question. If the adjustable resistor is adjusted to, we have this adjustable resistor. Let me, we have this adjustable resistor. Now we want to see if it is adjusted to question 1, if our adjustable resistor is equal to 175 ohm, what will be the rotational speed of the motor at no load? First of all, are you able to identify this circuit? Which configuration is this circuit?
Shunt motor, sir.
Shunt motor, exactly. Now, what will be the effect of changing the adjustable resistor?
Field current will change, sir.
Field current will definitely change, yes. So let us solve it. So earlier the field current would have been how much? Vt divided by Rf, right? That would be equal to how much? 240 divided by Rf is nothing but 75 ohm, right? So it will lead to much? 75 240. It will be equal to 3.2 ohms. Sorry, 3.2 amps. So 3.2 amps, are you able to see in the magnetizing curve?
No, sir.
No. So it means that current is not a feasible current for this particular core of the machine, right? Because this magnetizing curve is based on the core of the machine. If
Okay,
your
sir.
core is large, it means you are able to supply your flux proportional to the current up to large extent. But here, it is not able to take that much of current. So to limit that below 1 ampere or 1.2 ampere, we have to add some resistor, and that will be your adjustable resistor, and its value is almost higher than 2 times. So let us see what will be its value. 240 divided by 750, 75 plus 175. It will be 240 by 250, that will lead to 0.96 amps. Now you can see 0.96 amps. 0.96 amps. Let me zoom it for you. 0.96 amps will be it will create voltage of how much? You are able to see any close value would also work.
240 around.
240 volts. So to be precise, it is 241, but we can say 240 is good enough. So EF at this field current, EF is 240 volt. Sorry, 241. Let us go ahead with 241 volt at a speed of how much? This speed is given, that is 1800 RPM. Right? This speed is 1800 RPM. So what will be the rotational speed? Okay. So the thing is, in this question, at this field current, since we have reduced the field current, right? Since we have brought down the field current, we have certain limitations. So earlier the voltage was equal to V by I. Anyway, so we have to find the rotational speed at no load when 175 ohm is added. So when 175 ohm was not added, right? So at that time, VT was 240 volt. And when 175 volt is added, then we are not able to find out the voltage because it was exceeding the 2 amps, right? So now it will be equal to, since the speed we are not changing, we are keeping it fixed because we are varying the field. So we have two types of control, either speed control that depends on flux and current, right? So below base speed, you have to maintain the constant flux, right? Constant flux. But since you are reducing the flux below base speed, it means uh, you will be not able to utilize your all voltage. So here we are reducing the flux or field current directly. So IF phi f is nothing but is equal to KIF. So it will be linear. So that is the thing, that the rotational speed you are keeping the same, but you are reducing the field current, and that will lead to reduction in your induced EMF K phi f omega. So we have two cases, E1 by E2 equal to phi f1 into omega 1 divided by phi f2 into omega 2, which will be again directly proportional to if1 into omega 1 divided by if2 into omega 2. So in first case, it is given 240 volt, right? First case, when we haven't done anything, our phi is 240 volt, that will be equal to E when no load is there. If you apply KVL, so some current will go and some other current, if you apply this loop, armature current will be equal to 0. This whatever line current will come, that will go into the field. So your EF E1 will be equal to how much your E1 will be?
VT.
VT, that is 240 volt. And omega 1 was 1800
18.
RPM.
Yes.
And IF1 was 3.2. Now we have phi f2, which means indirectly we have phi f2, that is IF2, that is equal to 0.96. Omega 2, we need to find it out, right? And E2 will again, how much will be E2?
Mm,
Okay, let us see.
Sir, here E2 we have calculated 241, sir.
E2 we have, yeah, actually we have calculated E2, right? According to it. Yeah, so that is 241. Yeah, thanks for pointing it out. 241 volt. So very minor change. Now we can compute omega 2. So omega 2 will be 1800 into 241 divided by 240. So it will be equal to,
Sir.
yeah, go ahead.
So this machine is operating as a motor, sir. Sir,
Yeah, yeah.
sir,
This
for
machine,
motoring operation, sir, the induced voltage cannot be greater than the terminal voltage, the applied voltage, sir.
in motoring. Okay, let me write the expression Vt is equal to EF plus,
IR.
yeah.
So
So
the terminal voltage is 240, but the induced voltage is 241.
yeah, so that should not follow, right?
At most, it could be equal, but it cannot be greater than that, sir.
Right, 240.
Sir, I
That
think
is
Deepak was
correct.
saying something, sir. Please take his question, sir.
Okay, let me see. At no load, armature current will be zero. Rotational losses is given in the problem. At no load, armature current will it be zero? Rotational losses. Yeah, see, armature current will be zero, but some current will be drawn from the supply, right? To provide the losses and to rotate, right? Because if no current will be provided, then some current must flow into the field winding to generate the flux to rotate it at no load, so that EMF will be induced. So current might not flow, but rotational losses will be there. Okay.
Sir,
Yeah.
at no load, there should be current to produce a field current or to produce field flux and armature flux.
See, here in this shunt field, your connection in a way that even if you do not provide any current, there will be some current flowing in the shunt winding, right? Or shunt parameters. Because you have some voltage you have applied, so some current will be drawn along this voltage, along these resistances. So, and that is nothing but the field current. So field current should be produced to produce the flux in the machine.
Okay, and sir, IA will be some value.
IL will have some value. IL will have some value. IL will be nothing but it's equal to IA plus IF in this motor.
Sir, IA armature current should be have some value at no load.
No,
or
armature
not?
will not take any current. That will be zero. Yeah,
Sir, due to rotational losses, there is a loss of real power, sir. So the real power should be supplied.
yeah. So
So
that is nothing but EB into IF, whichever is going, right? That IL component will have only field component. So this will be VT into IL.
sir, to supply the losses, sir, there should be a EA into IA. So there should be some non-zero value to supply the rotational losses, sir.
Yes. You are correct. See, E is nothing but EB into IA at no load, and at no load, IA is zero. Sorry, let me EB into IL, right? So at no load, IL is equal to IF only, since IA will be zero now, and this EB also at no load will be equal to VT. So whatever power at no load, that is VT into IL, that is nothing but power going in your losses. But just that your IL is drastically low, terminal
So
voltage multiplied by the no load current provides. Yeah, no load armature current is what? IAO plus IF, no load current. Okay. I got your point. Hmm. So you are saying at no load, some portion should go here also, right? So that's why B into IA will be. That's what he's saying, right?
yes, sir.
Hmm.
EB into IA will be equal to 3,555 watt.
Ah, okay. Yeah. That one, yeah. That one will be there. Yeah. Sorry, I forgot that point. Yeah. So at no load to supply that losses, this EB into IA, that will be generated in case of rotation. So I think I have one question based on this same concept. Just let me take that problem and I should have one problem based on this. Yes, so let us solve one problem based on losses such that we will be well equipped with loss components. With these data only, right? No, I think Tyson curve is at 5. Okay, let me change the magnetization curve as well. Now this magnetization curve So let me provide you the data. 7.5 HP, 120 volt, DC series motor with armature resistance is equal to 0.1 ohm, field resistance is equal to 0.08 ohm, and at full load input current IL, okay, this is DC motor, right? I have written at full load the input current is 56 amps and the rated speed is nothing but 1050 rpm. Okay, magnetization curve is already shown. Core losses are 220 watt. Mechanical losses are 230 watt, and they are at full load. However, they are speed dependent, but still in the question, this data is given as a full load. And here we have to consider this speed or mechanical loss vary as the cube of the speed, and the core losses are the constant. So mechanical loss vary cube of the speed and core losses are constant. Okay, so these are the data. Now we have to calculate the efficiency of this motor. Okay, so for efficiency we can do output power divided by output plus losses. So P output we are given, right, 7.5 HP, and if you multiply with 746, that will be equal to 5.6 kilowatt. So we have output. Now we have to compute the input power. Okay, so input power will be equal to Vt into IL, right? So I think it is a very straightforward problem. 120 into 56, since IL was given. And since it is a DC motor, this IL will be equal to IA and field current. So it is very straightforward question. So I think I didn't pick this question. So, okay, so this is a DC series motor. So let us first compute the efficiency in this case, and let me get back to the shunt motor in a while. 5.6 kilowatt divided by 6.72 kilowatt. So it will be equal to 83%. Okay, any doubt in this part?
The efficiency, this efficiency at full load.
This efficiency is at full load. Yes, rated current of 56 amps.
Sir, if we want at particular load, then how can we proceed?
So see, a mechanical losses, you can see that it is a proportional of cube of the speed. So first you have to find out appropriate mechanical losses, right? And then at that load, what will be the copper losses? So yeah, Deepak, you are right. For losses, uh, output power plus losses also you can do. But since here we are given directly Vt and IL, so we can compute input power. Otherwise, you can go ahead with what approach? Since it is a DC series motor, IL square Ra plus IL square Ra. So it will be your copper loss, right? And core loss is already given in this problem. So that way also you can follow. Is that fine? Okay. So the next question is what will happen when load will vary, right? That was the question of Deepak he just asked. So part B is we have to find out the speed and efficiency of the motor at IA is equal to 40 amps. Okay. So now how to proceed? When IA will be 40 amps, we have to find out the speed and efficiency, and we have this data.
Sir, we can find out the EB and then we can find the speed at this current.
Yes, whenever we have to find out, back EMF, we have to depend on the speed. We have to relate the speed and back EMF. But okay, so we have to find out the EB at two different armature currents, right? So here EB, did we find? No. So let us find EB for first case. So EB1 will be equal to VT, that is VT minus IL or IA or IF, whatever. Both, all of them are in series. IL RA plus RF. So VT is given 120 volt. IL was 56 amps. RA is 0.1 plus 0.08. Yes? Yeah, 0.08 plus 0.1. So it will lead to one value. Please calculate it for me. Another will be EB2 for this particular case.
109.9.
How much? 109.9
9. 2.
volt. Okay, 92 volt. EB2 will be again 120 minus 40 ampere this time, and same 0.18. How much will it be? 7.2, 112.3. Is it right?
Yes, sir. 8.8.
Okay, 0.8. Now, corresponding to this voltage, the speed was how much? 1050 RPM. Right.
Rated speed.
Rated speed. Now we have to find this N2. So A2 by E1 is equal to N2 by N1. N2 will be 1050 into 112.8 divided by 109.92. How much will it be? Or are we doing correct thing? First thing you should always ask, are we doing correct thing? Then you let me know the answer. In shunt field, what we do, we always consider, since our resistances are connected in parallel to the supply voltage, that our field current are constant and we are having constant field supply. But in series, when you are varying the load current or input current, what indirectly you are varying? You are varying the armature field as well and field flux as well, right? Are you getting my point? So here we left IF2 and IF1, didn't we?
Yes, sir.
Yeah, and this IF2 is nothing but IL2 and IL1. So again, we have to multiply it with IL and 2 is equal to IF1 by IF2, and IF1 was 56, right? So it is 56, it is 40. How much it will come out to be?
Sir, speed is coming 1508.5. It is
5 hours.
increasing.
Yeah. So since we have reduced the load, so speed should increase. That is fine, right? Is it right?
Okay. Sir, speed is inversely proportional of current.
Of load. So as you reduce the load, your speed should increase, right?
Okay. Sir, if
Hmm.
torque will increase, then speed will increase or decrease?
If torque will
Torque.
increase and you have applied constant input, then your speed will decrease if you are increasing the torque, because power should be constant. To maintain the same power, if you are increasing torque, your speed should increase. And you are increasing torque means you are increasing current for the same power.
Okay.
But here we reduced, oh, so here we reduced field as well. So it is very good to think. Actually, see, this this question might have multiple answers. Let me again share it. This question might have multiple answers. It might have two speeds, one corresponding to a below base speed, other corresponding to the above base speed. So why below base speed I am saying, because this is a machine, and here below base speed, if you are reducing the flux indirectly by reducing the line current, what you are doing, you are reducing the torque of the machine below base speed. But at above base speed, you are again doing the same thing, right? You are reducing the field current to operate it into the field weakening mode. So it's very interesting to think. You think about this point, okay? That what could happen? Have we considered all the scenarios, right, or not? So it might be one part of this question, this answer, and other part of answer should be also there. So please think about it, okay? And let me know what other solutions you have come up with. So this speed from this answer, you can see that it is higher than the rated speed. So it from this solution, it appears that it is in field weakening, right? But there could be another answer which could be below the base speed with low torque capability. Does that make sense?
Sir, I didn't get your point.
See, here field current and armature current are codependent. Essentially, they are identical. Okay, in this particular problem, since it is a DC motor, right? Am I right?
Yes, sir.
Okay. So you
Core
can consider the
dependent.
codependent means both are interdependent on each other. If you change line current, indirectly you are changing field current. If you try to
Yes, sir.
change field
Yes.
current, you are
Okay.
indirectly changing the line current. So
Yes,
what
sir, because
happens?
this is series motor.
Yeah. So what happens that when you want to operate it into field weakening, okay. So what will happen if you want it to operate in field weakening, or whether it is capable to operate in field weakening? First thing that you should uh, ask yourself. And second thing, if you are reducing field, whether you are reducing field below pressure speed or above pressure speed. So that you have to find out. If you are reducing field below pressure speed, it means you are reducing the power of the machine. Because below pressure speed, your speed is base speed till base speed, it is constant, and you are reducing field, it means you are reducing line current also. It means you are reducing torque. So torque and omega, torque is reduced and omega is constant. It means power is reduced. So that's what you are doing. Another way is, if a speed is higher than base speed, you are reducing flux, okay, which will lead to reduction in line current, okay, which will reduce your torque, but your speed has been increased. So what will it lead to? Close to constant power, right? Or or not, or not. If your ratio of decreasing is not equal, then what will happen? The rate of decrement in torque will be twice of the speed. Why I am saying this statement? Because torque has two components that is reducing, flux as well as current, right? Torque is equal to K phi Ia. Ia is also reducing, phi is also reducing. So if this reduction, combined reduction, right, or which will be equal to K Ia square, this Ia square should reduce such that omega increase. If Ia square omega is equal to constant, then your power will be constant. Does that make sense?
Yes, sir.
Yeah. So on the basis of all the possibility, you have to figure it out what could happen, what could be the value of the speed of this particular question. Am I right?
Yes, sir.
So please think over it, think over this particular question, and from next session we will catch it up from this point. Okay.
Sir,
Hmm.
here whole problem is not given
Here,
statement.
where?
Sir, in this problem, statement is not given.
Yeah, in this problem, I have written that we need to find out the speed and efficiency at 40 amps. So let me show you. If
Okay.
you will go through the PDF, you will find it out. Yeah, part B, a speed and efficiency of the motor at this current. Are you able to
Okay.
see?
Okay.
Yeah,
Yes, sir.
yeah.
Okay.
So
Thank you, sir.
thank. Have a good night. Bye.
Bye.